rate curves. Let's do both of them in one, right? No. Normally, as I said before, can be concentration here, right? Versus time. So time is always on the x-axis, right? So time will always be here. But on the y-axis, it can either be concentration, or volume, or mass. Can be on this axis, alright? So let me just write the possible units that we have here. So time will, SI unit is seconds. So here is concentration, will be moles per dm cube, or it can be volume, like cm cube mainly they will use, or it can be mass. And this will be in grams. Alright? The change in products versus time. So they have to be specific, right? Based on how the shape will look, right? So if it's a change in products, it means that products are being formed. So definitely the curve will be like this. Now, what do we notice here, right? Because technically this is a graph that you can get to discuss. Actually, this should be horizontal. Remember, I'm drawing with freehand, but this should be like a horizontal line here, right? So this is a graph that you normally would get in the exam. You can plot it first and then they'll tell you to discuss it, right? You could also technically use it to find a volume of gas that's produced if you're using a gas reaction, right? Now, if you notice this curve, initially, say for example, we're talking about concentration here of solution. When the concentration initially is high, you find out that the rate is faster. But as the reaction goes on, you find out that the concentration of the reactant would be decreasing, and hence the rate would actually be decreasing. So the initial aspect of the graph should be the steepest. But as the reaction goes on, the curve will start to get like, what should I say now? Like less steep, so shallower, alright? So initially it's steep, then it becomes shallow, and then it will actually level off. We call it plateau, alright? So those are the different aspects of the graph you have to discuss. Like the initial aspect here is steep. Here becomes shallow. Right? And then finally we'll have the horizontal aspect, right? Right? So here initially this aspect is when the concentration is high. So initially you'll have this part of the graph is steep. As the reactants used up, then it becomes shallow. As you can know, it's not as steep. And then finally when the reaction is finished, say for example at about this time you realize that the reaction basically stops. So we won't have the gradient being increased. Because really the gradient we look at when we plot this graph, alright? And so here, if we should plot a graph in the exam, if we should extrapolate this horizontal line here, we'll either get the volume of gas that is produced, because remember that this is a change in products, right? Or the final concentration of the product that is produced, or the mass of the product that is produced. Those are the stuff that we can get from this graph. Alright? But mainly, when we are using this particular graph for the product, it's mainly when gas is being formed, we use the products mainly. Right? In terms of mass, it's mainly the reactant we use for the mass. Because how it goes when we measure in mass is that if the gas is produced from the reaction mixture, then as the gas evaporates, we expect the reaction mixture to get lighter and lighter. Following, we can know that the gas will escape with some of the weight that is produced, so the reaction mixture will get lighter and lighter. Right? Which the graph will look at in the opposite direction. Right? Alright, now, say for example, we add the factors, so we increase concentration, increase temperature, we add catalyst, we increase surface area. Right? This is how the graph would look. So, the initial aspect of the graph, the rate would be faster. But the important thing to note here is that it's still gonna plateau and become horizontal at the same level. As in, because what happens is that if we should vary these stuff, we're not really increasing the limiting reagent. And what do I mean by a limiting reagent? Normally when a reaction is we mix two substances in a reaction, the number of moles of one of them will finish before the next reactant. The one that's used up and finished completely, that's called the limiting reagent. The one that is left over, the reactant that is left over is the one in excess. So whenever you talk about limiting reagent, it's actually the reactant that is completely used up in a chemical reaction. While the one in excess is the one that is left over after the reaction is complete. Because remember that if, for example, we have a solution with some acid and we drop a piece of metal in there. If the acid is in excess, if the number of moles of acid that is there is higher than the moles and the metal, then the metal will completely react until it disappears. And the reaction will stop. And excess acid will be there in solution. So the metal in that case will be the limiting reagent because it is the one that is used up fully. Right? If the acid in that case is the limiting reagent and we should put a metal strip in the acid, then what is going to happen is that after the reaction stops, a piece of metal would still remain in solution because there probably be no more H plus ions to react with the metal. In that case, the metal will be in excess, the acid is the limiting reagent. So, any one of the reactants can actually be the limiting reagent. Right? And limiting reagent is just simple, the reactants that is used up first. That is finished. Right? So, as you can see here, basically, if you're asked to discuss a graph in which we increase one of the factors that speed up the rate of a reaction, this is how you will plot the graph. Or to sketch it to show that it's actually steeper initially, showing that the rate is faster. But eventually, if the volume of gas produced or the final concentration is actually going to be the same, because actually in most cases, you're not really interfering with the limiting reagent. That's a thing to know. If you don't interfere with the mass or volume or the amount of substance at the limiting reagent, both the catalyst or whichever factor you use to increase the rate of the reaction, it actually level off at the same volume, concentration or mass that is here. Following? Good? Alright. We're in So we're looking at question number 6, page 120 from the concise chemistry revision. Alright? Now it reads the graph in figure 6 shows the result of an experiment to determine the rate of a reaction between calcium carbonate crystals and nitric acid. The experiment was carried out at room temperature and pressure, RTP, by adding a fixed mass of crystal to excess acid of concentration 0.5 moles per dm cube. The graph volume of gas produced against time is shown in figure 6. Alright, so as you can see on the graph there, the volume of gas produced, they have on the scale, the y-axis 50, 100, 150, 200 to 250, right? And the time is in seconds, 30, 60, 90, 120, 150, 180, 210 seconds, right? And if you can see the graph, there is that's a typical rate of reaction curve graph in which initially it's the steepest aspect, then it gets shallower, and then we have a horizontal aspect, which is the plateau, alright? And so 6A1, using the data from the graph, determine the rate of the reaction in centimeters cube per second in the first minute, and in the second minute. So first minute is equivalent to what? 60 seconds, right?
Yes, sir.
So rate of Rxn, so they want this in centimeters per second. So it is really the volume of gas produced over time, right? Volume of gas or time taken. Right? So the first minute. So if we look at 60, so you have to use like if you're in the book, they would actually, because I photocopy it's not so accurate. But if you should look at the graph like this, so you have like 30, 60, 90. So the plateau basically at about 120. Right? And then here is really approximately 200, 250. Right? So for the first minute you would go, this is how we do it in the real graph paper. So we look at 1 minute here to 60 seconds. We draw a line and then we go like here. Right? Do the same thing for the second minute would be what? 120? 60 and 60, 120. Do something like that, right? So when I was working it today from the stuff, I got in the first minute, the volume of gas that I got here was 130 divided by 60 seconds, right? This, what's the answer here? 130 divided by 60, 2.17 cm cube per second, right? So at 1 minute, the volume of gas that is being produced is 2.17 centimeter cube of the carbon dioxide gas is produced per second, right? At the second minute, so this is going to be over 120. I got approximately 200 cm cube of gas. This I got 1.67 cm cube per second. Right? Now, so after we do the calculation in part A1, that's two marks, right? It said to explain why the rate of the reaction changes from the first minute to the second minute. Who would like to try? So the rate of the reaction decrease. Agree? Because in the first minute is 2.17 cm cube of gas is being produced. By the second minute, it's just only 1.67 cm cube of gas being produced per minute. So you can see that there is an obvious decrease in the rate of gas that is being produced, and hence the rate of the reaction.